Chapter 6, we are still working on solving trigonometric equations. At this point, we are in the third section. So they're calling this Trigonometric Equations 2. 6.2 is Trigonometric Equations 1. And in each of these final sections of Chapter 6, sections 2, 3, and 4, we are basically just looking at examples of solving trigonometric equations. And so what they're going to examine in this section is equations with half angles, like theta over 2 or x over 2, and equations with multiple angles, like 2x or 3x or 2 theta or something like that. So let's take a look at some examples they have here for us and see if we can think them through. In example 1, the equation we are looking at solving is right here. 2 times sine of x over 2 equals 1. And in part A, they want us to solve this over the interval from 0 to 2 pi. And then again, this is for x. So that means 0 is less than or equal to x is less than or equal to 2 pi. And it's kind of important to realize that that interval is a restriction on x, because actually what's in the sine function is x over 2. Normally, we would look at the interval from 0 to 2 pi and think, oh, that's one period of the sine function. But when x goes from 0 to 2 pi, x over 2 only goes from 0 to pi. So they illustrate that in this first line here. So when you have this restriction on x, 0 is less than or equal to x less than 2 pi, if you divide all of these by 2, you realize that that means that 0 is less than or equal to x divided by 2 is just less than pi. And so we're going to need to take that into account. And so then when we go to solve this equation, we still isolate the sine function. So they took the equation, here it is. Oops. They divided both sides by 2, and that got them that sine of x over 2 is equal to 1/2. Well, as we want to solve that, we then consider what angles x over 2 would give us 1/2 in the sine function. And as we now know at this point that over the interval from 0 to pi, in quadrants 1 and 2, the place where you get the sine values of 1/2 are pi over 6 and 5 pi over 6. But these values are equal not to x, but they're equal to x over 2, because that's what was in the sine function. Let me just erase some of this clutter here. And so what that means is that x over 2 is equal to pi over 6, or x over 2 is equal to 5 pi over 6. And in those two circumstances, we can then solve and see what x would need to be. We would multiply both sides by 2 to solve for x. And that leads us to these two possibilities, that x itself is equal to pi over 3 or 5 pi over 3. And so these are already fitting in the range that were in the restrictions of 0 to 2 pi, because the solutions we took for x over 2 were between 0 and pi, and that assured that these answers for x are between 0 and 2 pi. And that's why we did that change of restriction. And so that ends up being our solutions. That's part A, that we get these two values for x will work. And again, you can check these. You could plug it in for x and confirmed that it works in each of these cases. But this is a good starting example. Now, for part B, instead of just having these two solutions, we want to find all possible solutions. All solutions for part B. So how's that going to change things? So they give us this way to try to explore this on a TI calculator, which you may or may not be using for this class. Most students are not. Most people are using like Desmos or something that's free that you don't have to spend $100 for. So we're going to kind of ignore how you would use a scale, X scale, and do these things. But in general, the part we want to focus on, which we can determine and didn't need the calculator or wasn't done on the calculator anyway, is that the sine curve that we have in this situation, if we consider this graph, because, well, we just remember that if you have this graph, if you look at the argument in here, when you have x over 2, that leads to a period of 4 pi. That means sine of x over 2 is going to repeat its values every 4 pi. And that means if we take our root solutions that we found in part A, which was pi over 3 and 5 pi over 3, then we can produce additional solutions to the equation by changing by the period of sine of pi over 2. And so we get the infinite solution set by simply taking the root solutions and adding multiples of 4 pi. And again, the way we write that is by saying plus 4n pi, where n is any integer. And so in this first problem, we looked at how to handle when you're solving an equation with a half angle in it. So this was the key thing to think about what we were trying to figure out here with a half angle. Now, for some reason, it says using a half angle identity. So if you come back to these slides, I just want to point out we didn't use a half angle identity here. So I don't know why they put that in there. But we did have a half angle in our trig function, and we had to deal with that appropriately when we were finding root solutions. So these were root solutions here. And then also, if we want to find all solutions, then you have to consider the period of a sine or your trig function with the half angle in it. That you recognize that we're not just going to go with the standard period of the sine x function, because when you have sine of x over 2, the period then becomes 4 pi instead of 2 pi. All right, now moving forward, we now are going to consider the opposite sort of situation where instead of having a half angle formula, we have a multiple angle, or in this case, a double angle formula. And so they in this case also say using a double angle identity. And you don't have to use a double angle identity in every case. We're going to in this case, but in general, let's just consider for a second that if this first problem that we had worked at had instead had 2 sine of 2x equals 1. Well, again, in this case, we wouldn't have needed to use a double angle formula, just like we didn't use a half angle formula on this example, because you can immediately solve for sine by dividing by 2. And then that would lead us to trying to figure out when is 2x equal to the inverse sine of 1/2. And then we just would have dealt with the 2 directly, and we wouldn't have had to convert it. Now, I'm just pointing that out because in their example 2 here, we don't have that situation. The situation is a little worse. We have a 2x in cosine, but we also have an x in a cosine. So when you have cosine occurring twice in the equation, we somehow need to get it so it only occurs once so we can solve. And the problem is that we can't combine these together because one's got a double angle and the other one doesn't. So for that reason, we're going to need to use a double angle identity to convert the double angle argument into just a regular x argument. And so they're using the double angle formula for cosine of 2x that would convert it into 2 cosine squared x minus 1. And notice here we have the double angle, and then here we have a single angle. And so if we use this to convert the double into a single, then in the equation you won't have any double angles left anymore. You'll only have single angles. And then when you just have cosine x in different places, you can try to solve that. So that's the motivation they have here. They just kind of do it without explaining it, but that's what you want to think about. If you see that you have a problem because one trig function has a double angle and there's another trig function that doesn't, well, then you need to make them so that they all have the same angle size measurement. And in this case, we can do that by converting the cosine 2x into an expression with just cosine x in it. So when they make that conversion, we go from having a double angle and a single angle cosine to having a little bit more complicated equation, but it's all in terms of cosine x. And at this point, we want to recognize that this new equation we have is in a quadratic form, which we discussed in 6.2. And then when we have it in quadratic form, we're going to set the equation to 0, so that we can sort of put it in ax squared plus bx plus c format. And if possible, when it's set equal to 0, you'd like to try to factor it directly, which they're able to do in this case. So in this case, they're factoring in order to use the zero product rule, also like we talked about in 6.2. If we hadn't been able to factor, we could use the quadratic formula to give us our two solutions here, but we're able to factor here. So then by the zero product rule, either the left factor equals 0 or the right factor equals 0. Then each of these are linear equations in cosine x, and we can solve by isolating cosine. So on the one on the left, we get cosine x equals -1/2, and on the one on the right, we get cosine x equals 1. And these are both results for cosine where we know what arguments will work. And we also respect the fact that the x value has to be within one rotation on the unit circle from 0 to 2 pi. And so to get -1/2, that actually occurs in two places at 2 pi over 3 and 4 pi over 3. However, to get cosine is equal to 1, that's only going to happen when you're at 0 over the 2 pi range, not including 2 pi. And so we end up getting two solutions from the left factor and one solution from the right, leading to this solution set they show here with exactly 3 values in it. So the key thing I would want to point out here in terms of strategy that they're illustrating in this second example is that they were able to take a double angle incidence of cosine and reduce it to a single angle incidence so that the entire equation only had cosine x's in it instead of cosine 2x's, and that allowed them to factor and solve. So let's see if we can go through another one here. So we have example 3a, apparently. Here we are using a multiple angle identity. So in this case, it's interesting. They kind of use it in the other direction. So let's compare and contrast 3a here to the 2 that we just did. In number 2 here, we got rid of a double angle and converted it to a single angle, because then everything was just in terms of cosine x. So what is our issue in this equation we're trying to solve? So here's the equation. Well, in this case, we don't have any double angles. And so why would we want to consider using a double angle formula? Well, the reason is that our problem in this equation is that we have two different kinds of trig functions that are multiplied and not equal to 0. And so, as we said before, if you have different trig functions, you either need to factor them out when they're equal to 0, which in this case won't work well because the equation is not set to 0. And if we set it to 0, we can't factor anymore. And secondly, if that's not the case, you might want to consider trying to get it so instead of having two different trig functions, you somehow have a single type of trig function. So I could say I'd really like to either have only sines or only cosines instead of a sine and a cosine. And so in this case, since we have a product of sine and cosine, one of our double angle formulas off here to the right for sine is that sine of 2 theta is equivalent to 2 sine theta cosine theta. So in this case, instead of getting rid of a double angle, if we take this formula and convert from left to right, we get rid of having a sine and a cosine and instead only have a sine function. And that solves the problem that we have in this particular equation that we need to overcome. And so that's what they do. They say, all right, well, they could have divided both sides by 2. In this case, they factored the 4 into a 2 times a 2, simply so that we could get 2 sine theta cosine theta and recognize that that part directly can be converted into sine of 2 theta using the double angle formula for sine on the right here. And so what did this accomplish? The big thing this accomplished with the use of this theorem is before it, we went from two different trig functions to only one. We went from two trig functions to one, a sine and a cosine, then ended up just having a sine function. And if we have a single sine function, it doesn't really matter if there's a double angle. That's what I was saying up here. If we had just had, like in the very first example I sort of said, if we had just had an equation with a single occurrence of a trig function and a double angle, well, then we don't really care that there's a double angle. And we were able to get to that point in example 3a. So in example 3a, we were able to get it to the point where we have a single trig function. And then at that point, we isolate the trig function. So they divided both sides by 2. And now we're considering when does sine of some angle equal square root of 3 over 2. But we have to consider that 2 times the angle is square root of 3 over 2 when the angle itself is anywhere from 0 to 360 degrees. So first we'll deal with this restriction on theta. Restricting theta to 0 to 360 degrees to see how that affects 2 theta so we can find what sine angles we need here. I would get theta to be 2 theta by just multiplying everything by 2. If I multiply 0, theta, and 360 by 2, I get that 0 is less than or equal to 2 theta is less than or equal to 720. And so when I find 2 theta or double theta angles for sine that give me square root of 3 over 2, all the ones between 0 and 720 degrees will end up giving me theta values that are between 0 and 360 degrees. And so they basically just, again, do this kind of with guess and check because square root of 3 over 2 is one of our nice results for a sine function. And we kind of know where that happens. That happens at like pi over 3 or 60 degrees, 2 pi over 3 or 120 degrees, etc. And if we get the first root answers, so these would be the root solutions. These are the roots here. But since our restrictions on 2 theta now run all the way up to 720, the root solutions aren't enough. They're not everything that's in there. To get the ones that are more than 360, we add 360 to each of those. So the 420 degrees here, they got that by taking the 60 and adding 360 to go around the circle again to get to that same angle. And then to get the 480, they took the 120 root solution and added 360. Now, if we were to add 360 again to either of those, we'd go past 720 and that would be too much. So by taking the 2 root solutions, the ones in one cycle around the circle, the ones between 0 and 360 that give you square root of 3 over 2 for sine, 2 theta could be 60, 120, and then by adding 360 to both of those, 2 theta could also be 420 or 480. Now, in the end, that tells us what 2 theta would need to be, but we're supposed to solve for theta, so we divide everything by 2, and then those 4 answers for 2 theta translate into these 4 answers for theta, 30, 60, 210, and 240. And that's the solution set. So there were 4 solutions. And again, you could check any of these by plugging them into the original equation and making sure that you end up with square root of 3. Let's try that just once. Why not? Maybe just change the color here real quick. So checking, let's just check 30 degrees. So if I take 4 times sine of 30 degrees, cosine of 30 degrees, I've plugged 30 degrees in for theta in both places, and I'm hoping to see that it comes out to square root of 3. So that would be 4 times, and sine of 30 degrees is square root of 3 over 2. And cosine of 30 degrees is 1/2. And we see that the two denominator 2's cancel with the 4. And then if you multiply straight across, you get square root of 3. And that checks. So there's an example of how by hand you could check any of these measurements and see that they work. Any of these degree measurements, these solutions. All right, maybe we'll see if we can take a look at one more here for this video. We have 3b. Well, actually, this is a good one because this is just an extension of what we just did. I wasn't paying attention. All right, 3b, it says now find for all solutions. So we had the root solutions for 2 theta. So they're going to pick up from where that left off. All angles 2 theta that worked in the, let's remind us what we had. Sine of 2 theta had to equal square root of 3 over 2. So we ended up getting the equation to sine of 2 theta needs to equal square root of 3 over 2 in part A. And so that led us to 2 theta needing to satisfy that the sine function gives me square root of 3 over 2. And that happens with 60 and 120. And again, I refer to these as the root solutions. So what that means is if I take those root solutions for sine and I add the period of sine to any of those, then 2 theta in that new angle will still give me square root of 3 over 2. So that means that 2 theta can be equal to 60 plus any multiple of 360. And also 2 theta could be equal to 120 plus any multiple of 360, because if you add multiples of 360, then that new result for 2 theta will still give you square root of 3 over 2 when you plug it into the sine function. Now we then take those multiple solutions, those infinitely many solutions that would work for 2 theta, and express them in terms of theta by simply dividing everything by 2. So if I take 2 theta is equal to 60 plus 360 times n, and I divide everything by 2, then all 3 terms are divided by 2. So I end up getting that theta is equal to 30 degrees plus multiples of 180. Multiples of pi instead of multiples of 2 pi. And that's because basically the period of sine of 2 theta is different than the period of sine of theta. And now you're getting repetitions every 180 degrees. When you multiply the inner argument by 2, that divides the period by 2. And instead of having a period of 2 pi, you end up with a period of just pi, or in this case, 180 degrees. So that produces our solution set. And in set builder notation here, written correctly, we would say that we have 30 degrees plus multiples of 180, 60 degrees plus multiples of 180, multiplying by n, where n is any integer. All right, let's see if we can take a look at one fresh example. So in example 4, we have kind of an ugly looking equation here, just to give my own personal opinion. We have tan of 3x plus secant of 3x equals 2. And we want to solve this over the interval from 0 to 2 pi for x. All right, so it says one way to begin is to express everything in terms of secant. So why would you know to do that? How would you know to do that? What's going on there? What's their motivation? So we have 2 things going on here. We have a multiple angle, but at least all the trig functions in here have the same multiple angle. Both the trig functions have 3x in the angle. So that doesn't seem as bad. But then we have 2 different kinds of trig functions. And that's the big thing. So if I have sines and cosines, then somehow I want to get it all in terms of sine or all in terms of cosine. In this case, if I have tangents and secants, then I'd really like to try to get everything in terms of tangents or everything in terms of secants. So what we did before to accomplish that, just to sort of show that we accomplished that goal before, was we used this double angle identity where a sine and a cosine that were multiplied together could be converted into just a sine function with the double angle. but these aren't multiplied together, they're added. And so we have to figure out, well, how could I convert one of these to the other? Well, this will most likely go back to our fundamental identities. Remember, you have sine squared plus cosine squared equals 1. And then you have additional identities off of that that allow you to go between tangents and secants or cotangents and cosecants. And so the one for tangent, which they have it down here, but this is as if you got this far, you'd already have to know that this is what you were looking for. So let me show you. They're listing it down here. Tan squared theta is equal to secant squared theta minus 1. So because they are anticipating using that, they're going to proceed the way they did. And so you kind of have to understand where their motivation came from. So the idea, here's the idea, and then that'll lead to what they do. Convert tan 3x into secant 3x or vice versa. So the idea is when you're looking at this equation, you think, how can I proceed? Well, I have tan and I have secant, and I really just want to have one kind of trig function. But I know with one of our fundamental identities that I can convert tan to secants or vice versa. And the thing then to remember is when you do that, the tans and the secants are both squared. It's tan squared plus secant, tan squared equals secant squared minus 1 is the version they have here, or secant squared equals tan squared plus 1. Either way, they're both squared. So because they're both squared, the way we could try to get it closer to that to make that conversion is we can square both sides. So when you square both sides, it will be easier and you won't get sort of products of trig terms if you have one trig term on one side and the other trig term on the other side. And so they begin by splitting their trig terms, the tan and the secant, on the two different sides of the equation. So I'm going to put here that what they did here is they got one trig function on each side. That's why they did that first step. They just do it. They don't really say why. It says one way to begin is to express everything in terms of secant. Why is that? Well, it's for when they square both sides. So when they do that, they get tan of 3x equals 2 minus secant 3x. Then they square both sides. And when you square both sides, on the left side, you're just immediately going to get tan squared, but on the right side, you have this binomial squared. And to figure out what's going on with the tan squared and the secant squared, you're going to have to FOIL that out. So they FOILed out the 2 minus secant 3x squared to get this sort of trinomial in secants by FOILing. So that was this step. They multiplied out, or FOIL is first, outer, inner, last, back from algebra. They FOILed the binomial. They FOILed the binomial of 2 minus secant 3x quantity squared. Because now when you've done that, you have a secant squared 3x term, and you have a tan squared 3x term, and that's where we can try to use the identity to try to work with those. So recognizing that, since you have a bunch of stuff in the right with secants, and you only have the tan squared on the left, if I were to convert the secant squared on the right into tangents, it wouldn't get rid of the secant in the middle term. So instead, we choose to convert the tangents into secants, because then the entire equation will only have secants. So using the tan squared theta equals secant squared theta minus 1, they then are able to convert tan into secants, so only secants remain in the equation. Once they've done that, they then have a big equation with only secants in it. And it turns out in this case that after they've done that, when they simplified, the secant squareds actually went away. Now, even if you had been left with a quadratic form of secants, then you could have solved using the zero product rule or the quadratic formula or something like that. But in this case, when they simplified it, the secant squareds 3x's on both sides just dropped out, and they got all the way down to this nice, simple, single equation only in secant. And now this is in a linear form, and so we can solve by dividing by 4 and trying to solve for the 3x in the secant from there. So that's a lot to sort of navigate through to begin working on this problem. And the big thing here is that they don't really show initially how they knew to do these steps. So you have to kind of ask yourself, if I was looking at that equation, would I be able to come up with a strategy of how to start manipulating it to try to reach a goal of solving the equation? And the big idea that I'm suggesting that we consider here as the strategy that they're emphasizing is that you want to think about converting the tans into secants or vice versa. And in this case, we ended up converting the tans into secants. We could have gone the other way if it would have worked better, but tans into secants worked better in this case. Now, how do we solve this at this point? We still have to solve for x, right? Well, now it kind of goes back to what we had before. We have a multi-angle. And in particular, secant is just equal to 1 over cosine. And so if secant 3x is 5/4, then we can convert that into cosine 3x of 4/5 by just flipping both sides using the one of our reciprocal identities. And that just makes it a little nicer. So we don't have reciprocal and we just have cosine 3x. And so now, again, they originally told us that x had to be between 0 and 2 pi. So what does that say about 3x? What kind of angles for cosine to get 4/5 do I want for 3x? So to figure that out, again, you take the restriction on x and you convert that into what the restriction is for 3x. And the simple way to do that is to multiply all of these by 3. And that would mean that the restriction for 3x is that 0 is less than or equal to 3x is less than 6 pi. So when we find all angles for 3x between 0 and 6 pi that work in the equation, those will be all the angles for x that are between 0 and 2 pi that work in the equation. So they're sort of pointing that out. Multiply each term of the inequality by 3 to get this interval for 3x. Then how do we solve that? Well, now our issue is that 4/5 is not one of our friendly values that we can just kind of guess and check for cosine. So they sum it up. At this point, they said, oh, we've done this before. You did this in 6.2. So what do they say? Well, first of all, you're going to need to use a calculator because it doesn't come out nice. And the fact that cosine is positive in quadrants 1 and 4. And then boom, they say we have these 6 answers for 3x. So just to fill in a few of the details here a little bit. So the first thing you would do is the first answer you could get, the first root solution is you could take cosine inverse of both sides. And this leads us saying that 3x is equal to cosine inverse of 4/5. Now, when you take cosine inverse of 4/5, the restricted domain on the cosine function was that it's going to be some number between 0 and pi. So what we have here will be a number between 0 and pi, and that's the first answer they got. So in this case, 3x would be equal to approximately 0.6435, and that's how they got this answer. All right, so if I have that, well then how do I get those other 6 answers? How do I get more answers between 0 and 6 pi? Well, this was our first root solution. So I'm going to say root. We had 0.6435. But the way we get other root solutions, as we've alluded to in the previous section, is you have to kind of be comfortable enough with the cosine function to see how we can get another root solution. So let's illustrate that. Maybe purple. So again, if I'm thinking about the cosine function, and I'm trying to say, what could I get between 0 and 2 pi? The cosine function starts at 1, goes down below, and then comes back up to 1. Sorry for this crappy quick sketch. So we could say to ourselves, where is it that we would end up being able to come across 4/5? Well, if this is 1, then 4/5 is up here somewhere. And the cosine inverse function, it gives us that first answer between 0 and pi. That's the restriction for the cosine inverse. So the cosine inverse function gave us this answer. So this answer is starting from 0, goes to the right. I'm just going to put 0.6 just because I have a bad little picture here. 6435, something like that. So that first solution is 0.6 to the right of the 0 starting point in this 1 cycle range. And by symmetry, there's another root solution over here. And that first root solution came from the left border by moving right by 0.6. So the second solution we will find by backing up from 2 pi by 0.6 as well. That's the symmetry. So with a root solution of 0.6435, we have another root solution of 2 pi minus 0.6435. And that turns out to be the second solution they have on their list. So the second root solution is 5.6397. So we end up with 2 root solutions that are between 0 and 2 pi. Those first 2. Then the way we get the other 4 solutions they have there is we add multiples of 2 pi until we've gone up to 6 pi. So the second number they have here, we get by taking the first one and adding 2 pi. And then we go again and we add 2 pi again to get the next one. And if I added 2 pi on top of that, I would go past 6 pi, because if I add 6 pi to a number, I end up with more than 6 pi. Then to get the other remaining solutions, they took the second root solution and they added 2 pi to that, and then added 2 pi again. So the 2 root solutions between 0 and 2 pi produce 2 more between 2 pi and 4 pi, and another 2 more between 4 pi and 6 pi. And we get each of those by adding 2 pi to the previous ones. So this produces these 6 solutions for 3x, for the multiple of x, 3x. These are 6 things where if 3x is equal to those 6 values, then you'll get 4/5 out of the cosine function. So then lastly, to get that in terms of x, they take all 6 of those and divide by 3. So if you took everything there and divide by 3, then you get these 6 solutions here. And again, getting 4/5 is not a nice multiple, not a nice radian multiple of pi or something like that. But again, you can use the inverse cosine function to get the very first root, and then use symmetry and multiples of 2 pi to get the other solutions in the indicated restricted range of 0 to 6 pi for 3x. And that leads to these 6 solutions for x that are between 0 and 2 pi. Now, it also points out that in order to do this, what did we do? We did that thing that we warned about last section, just playing with my colors here. This one right here, we squared both sides. And whenever you square both sides and you get solutions because you squared both sides, you have to check the validity of your solutions. We discussed that in the early video about 6.2. And so here's the 6 solutions we got. But then it says, since the solutions were found by squaring both sides, we must check that each proposed solution is a solution of the original equation. Well, how do we check these nasty decimals? Well, you just plug them into the equation on a calculator. So they're illustrating that here on a Texas Instrument of some sort. Again, you could just do that on Desmos or even on any scientific calculator with a trig button on it, basically. And so let's take a look at how this showed up. So this is them checking the first value. So the first value is 0.2145. So they're plugging in tan of 3 times 0.2145 plus, and the next one was secant, so they're doing 1 divided by cosine of 3 times 2.145. And when they evaluate that, that's how they're evaluating this left side of this equation. And tan of 3x plus secant of 3x is supposed to come out equal to 2. So when they plug that in with that value, well, the calculator doesn't give you exactly 2, but it has 1 point, a bunch of 9. So that means because we have approximate solutions to 4 decimals, we're not expecting that it'll come out to be exactly 2, but we know if it's that close that the exact value would come out to be 2. Then so that confirms that the first solution listed is valid. But when they check the second solution, which was 1.8799, they end up with like a half, 0.5 and a bunch of zeros. And so that's not a 2. So that means we have to say no to that solution. And similarly, they check the third solution and it works. They check the fourth solution and it doesn't because it came out to be 0.5 again. They check the fifth solution and it works, and the sixth solution does not. So we have a selection that's working and another one that isn't. So you end up with 3 actual solutions because 3 of the solutions we got were false solutions because we squared both sides. When you square both sides to solve an equation, you will find any solutions there are, but with them may be some false solutions which have to be discarded. So in this case, there are 3 solutions in the indicated 0 to 2 pi range for x. And we found all 3 of them, but the way we solved it produced 3 ones that weren't true that we had to throw away. And so in the end, we have this solution set with at least a good decimal approximation of the 3 solutions for x to solve the equation that are in the range from 0 to 2 pi. Lot to think through there, a lot of ideas to try to practice on problems yourself. And that's plenty enough for this video. So we're going to stop there. So again, these were some problems for us to try to take a look at 6.3 and look at equations with half angles and equations with multiple angles. And we did several examples of those. So hopefully that helps. Keep up the hard work and reach out to me if you have any questions.